So in this section, we'll learn about all-pass filters, which are the basic building blocks for guitar effects like phaser, flanger, chorus, vibrato, etc. So we'll quickly go through the theory part. We will not go into too much of mathematical details, but I'll walk you through to the basic intuition behind these filters. So the all-pass filter, as the name suggests, has two functions. First, it should pass all frequencies. And the second aim of the filter is that it should manipulate phases depending on the frequency of the signal. So we'll just quickly revisit complex numbers. So if you recall, if there's a number like this, let's say there's a number z1, complex number z1, which is in this form, and we wish to find its magnitude. So the magnitude of this number will be nothing but minus a square plus omega square. And if we need to find its angle or argument, then the argument will be nothing but tan inverse of omega divided by minus a. Now assume we have another complex number z2, which is of the form plus a, and we do the same exercise here for both the magnitude and for the angle. So as you can see, its magnitude is nothing but a square plus omega square, and its angle is nothing but tan inverse omega by a. So this is straight away from basic complex numbers, and assume that we form a function, let's say hz, by taking the ratio of these two numbers, z1 and z2, and we calculate the magnitude of this function. So what we get is nothing but a square plus omega square divided by a square plus omega square. Both these terms are the same, so we will get 1 as the answer. Now this is very important for us because it satisfies the first property, where we said that no matter what the frequency is, the filter should pass all the frequencies without attenuation. So where is this frequency coming from? This omega is nothing but 2 pi f in signal processing terms, and this is where the frequency part is coming from. So this f is nothing but frequency of the signal, and if we are in digital domain, this will be written as frequency by sampling frequency. So this kind of, our filter should have this kind of a structure. It's very clear. Now, what about the phase? So when we do the argument of this function hz, so basically it is argument of z1 divided by argument of z2, which was nothing but tan inverse of minus omega by alpha, and since the denominator phase is an opposition, so this will be written like this, tan inverse omega by alpha. Now this particular term can be rewritten as minus tan inverse omega by alpha, and this term remains the same. So what it finally becomes is, now both these two terms are same, so they will combine together, and this is the final result. So this is the argument of a function like this. What do we infer from this? It's very clear. So when omega, which is in radians per second, and let's say phase, so when omega is 0, that means this term becomes 0, so the phase becomes 0, phase in degrees. So this will become 0 degree. As this omega continues to increase, let's say it goes to infinity, this phase is going to increase and it will reach minus 180 or minus pi. That's what is the implication of this formula. And once again, now from this table and from this expression, it's very clear that based on the frequency of the signal, and that frequency is coming from this omega, which is 2 pi f, based on the frequency of the signal, I'm able to change the phases. That means each frequency component goes through a different delay inside this filter. Only the phase of the signal gets manipulated, but the magnitude remains the same because the gain of this filter is 1. And that's exactly is the definition of all pass filter. So in summary, if we have a filter like this, whose transfer function can be defined like this, this is the transfer function. So my numerator is j omega minus 1, and my denominator is j omega plus a. This becomes the transfer function of the all pass filter, as we have seen above. And we know if you have to write it in Laplace domain, we know S is equal to j omega. The same expression in Laplace domain can be written as S minus a and S plus a. What does this mean? If we have to visualize it, then we know that in S domain, we can plot poles and zeros. So essentially, so this is my unity circle. Doesn't look too great, but let's just assume that this is a unity circle. So what does this numerator gives? Numerator gives us zeros of the system. And where is the zero? The zero of the system is at S is equal to a, which means the zero of the system is lying here at a. And we also know that denominator of the system gives poles. So pole will come from here. And where is the pole? Pole is at S is equal to minus a, which means here is the pole at minus a. And for the stability of the system, we know that the a should be chosen in such a manner. If you remember, the radius of this circle is 1. That's the reason why it's called unity circle. So for the system to remain stable, the poles and zeros of the system should be within, at least the pole should be within unity circle, which means a should always be less than 1. This a finally decides how quickly the phase of the signal changes, and we will see it in the next section. So basically we have, in this section, we have figured out a transfer function which meets the requirement of all pass filter, and I will continue this in the next section. So we have so far derived the transfer function of all pass filter in analog domain, and this is how it looks. Now if we have to implement this transfer function in digital domain, in digital signal processing, then we must convert this analog transfer function into a digital transfer function, which is essentially, it looks like this. So this is the digital version of it. I'm not going to get into the derivation of it, but it's quite straightforward. What instead I'm going to do is take this transfer function and derive the filter structure from here. So as you can see, this is in Z domain, and we need to convert this transfer function from Z domain to time domain so that we can implement this filter structure. So as we know, the transfer function Hz is nothing but Z transform of the output divided by the Z transform of the input, which is shown here. Okay, so now what we're going to do is we are going to take this denominator and we're going to multiply it with the Z transform of the output, and then we are going to take this numerator and we're going to multiply it by the Z transform of the output. So this is how it's going to look. So we have Z transform, and then we have this expression, basically the denominator, and then we have the numerator multiplied by the z transform of the input. Let me just expand this equation. So this becomes yz plus a z inverse y of z equal xz axz plus z inverse x of z. So now we need to take inverse z transform and convert this into a time domain equation. So if you remember the basic z transforms, if there's a y of z and if it gets multiplied by z inverse, when we take the inverse z transform of it, it's nothing but the delayed version of the y. Similarly, if we take xz and multiply z inverse with it, so in inverse time domain, it is nothing but the delayed version of xn. So we'll keep these two points in mind, and you will see that we are encountering these terms here. We would use these formulas here. So once we are doing inverse z transform, so this is how it's going to happen. Yz will become yn, and this will become a y n minus 1. This will be a xn, and this is the delayed version of the input, which is x n minus 1. So remember, this is what is our output. So let's arrange this equation. Basically, I'm going to take this part on the other side. So this becomes a xn plus the delayed version of xn minus a y n minus 1. So this is our final difference equation of the all pass filter in the digital domain. Now we have to come out with a filter structure, and let's see how to go about implementing this in a filter structure. So for that, I have created this filter structure, and essentially we have already covered this part, so this is not needed. I'm going to erase this. Okay, so I propose that this filter structure implements the difference equation that we saw earlier, which is this one, and let's investigate whether this is actually implementing this difference equation or not. This one, right? So let's see. So let me first define what is happening here. So this is input in time domain xn, and this is the output. This is the delay line here, and we have a multiplier which is multiplying the signal in this chain by minus a, and we have another multiplier here which is multiplying the signal with a in this particular chain, and then we have a couple of adders here. So let's see what let's analyze what's happening here. Let's say that signal at this point is Vn. So after passing through the delay line, it will be delayed by one sample, so it will be the delayed version Vn minus 1, and we take this signal and we multiply minus a with it. So what we get here is minus a Vn minus 1, and then in this adder, the input xn gets added with this signal, and that produces Vn. This Vn travels up the chain in the feed forward path. It gets multiplied by a, so it becomes avn. This avn comes and gets added here with Vn minus 1, and that generates the output. So basically we have two equations. The first equation is like this. So we have Vn here. So this Vn is nothing but summation of xn and summation of this minus a v n minus 1. So this is our equation number 1. And second equation comes from here, which is the output yn. Output yn is nothing but combination of v n minus 1 plus this component which is coming from top. So that is avn. So this becomes my second equation. And let's continue to simplify this. Now I'm going to extend this logic, this one, and take one step back. So firstly, what I'll do is that I can see that I have Vn here, I have Vn here, and I have Vn here. So I can do a straight away substitution. I'm going to do that substitution now. So let's do that substitution. So let A, and then this entire formula, which is xn minus a v n minus 1, and this is getting added with v n minus 1. Now after simplifying it, yn becomes a xn minus a square v n minus 1 plus v n minus 1. Basically, we have to get rid of these v terms because they are intermediate signals, and we have to rearrange this equation in terms of x and y, thus establishing the relationship between the input and the output. So this becomes my equation 3. Let's go back to these equations here, 1 and 2, and travel back in time. So this is Vn. I can take one time step in the past, and I can rewrite this equation like this. Vn minus 1 can also be written as x n minus 1 minus a v n minus 2. So why I have done this, if you see, this component can straight away be replaced by this expression. So this becomes my equation number 4. And also I can take one step back as far as output is concerned, this equation is concerned, and rewrite it like this. Y n minus 1 y n minus 1 equals v n minus 2 plus a v n minus 1. And I can simplify this further. Basically, I'm going to move this term on the left side. Y n minus 1 minus v n minus 2 divided by a is equal to v n minus 1. Why I have done this? Because I'm going to replace this v n minus 1 with this expression, which is my equation 5. So this will be replaced by 5, and this will be replaced by 4. So let's do that. So my yn now is, I keep the first term as it is, and now I'm going to use minus a and use this fifth equation here, which is y n minus 1 minus v n minus 2, this was a square, so a square. So this whole expression is divided by a. Here a and a get cancelled out, and now I have this term vn minus 1, and this gets replaced by this particular expression, which is x n minus 1 plus x n minus 1, sorry, minus a v n minus 2. Now as you can see, if I open this up, this remains the same. This becomes a y n minus 1. This becomes plus a v n minus 2. This remains just the same, and this becomes a v n minus 2. This term and this term, they cancel out. They're just the same but opposite sign. So what I'm left with is this. Y of n is equal to a plus x n minus 1, delayed copy of the input signal, minus a multiplied by the delayed copy of the output signal. So this is what is the difference equation, and this is exactly the same as, let's call it 6. This 6 is exactly the same as I had shown here. So again, a multiplied by the input plus delayed version of the input, and minus a multiplied by the delayed version of the output, which means this filter structure that we derived here, this is nothing but an all pass filter. And this section on top is called as feed forward, and this is called as feedback. So, and this eventually implements the transfer function is equal to a plus z inverse 1 plus a z inverse, which is what we are looking for as far as the transfer function of the all pass filter is concerned. So just remember this filter structure is very important, and this is what we are going to implement in digital code in Python.